Hi guys, we're back to talk about rocks. So I'm going to share my screen and we're going to start out by talking about igneous rocks. Is the slideshow going to start here? So first of all, just to remember, rocks are different than minerals because they are made up of multiple different kinds of minerals or an aggregate of many different minerals. But because they're made up of minerals, they have many similar characteristics in that they're solid, they're naturally occurring, and then they contain these different fragments of these kind of inorganic mineral structures. So here's a picture of granite, which includes some of these different minerals such as quartz, which is white, feldspar, which is kind of a brownish grayish color, and hornblende, which is a black color, as well as some other minerals. So there's 3 rock groups that we talked about when we talked about the rock cycle. And no, they're not classic rock, punk rock, and hard rock, but they are igneous rocks, sedimentary rocks, and metamorphic rocks. So igneous rocks are those rocks that we're going to talk about first that form from freezing or a solidification of magma or lava, which is just magma that starts to degas and come up to the surface. And then afterwards, in different videos, we'll talk about sedimentary rocks, which are cemented together or precipitated pieces of kind of older rocks that have been broken apart and transported across the landscape. And then metamorphic rocks, which are rocks that are changed as a result of heat and pressure in a solid state. So again, we're going to start with igneous rocks. And igneous rocks are rocks that solidify or form from freezing of a melt. And this can occur underneath the earth, below the earth's surface, or it can occur on the earth's surface. So those rocks that cool below the earth are sometimes referred to as plutonic because remember, Pluto was the god of the underworld. And more commonly, they're referred to as intrusive igneous rocks. So they form inside in the interior. And so there's that same root word of int for these intrusive igneous rocks. And they form relatively more slowly, as we'll talk about, and that causes them to have a different look to them, usually with larger grain sizes. So if you can imagine what a rock like granite looks like, that's a classic intrusive igneous rock. On the other hand, we have also rocks that can form from solidifications of melt on the Earth's surface, and this is usually when this melt is coming up from the interior of the Earth and spilling out onto the Earth's surface at volcanoes. So these are sometimes referred to as volcanic rocks or extrusive igneous rocks because they're on the exterior of the Earth. So this material forms more quickly. It cools off much more quickly in this cooler environment on the Earth's surface and forms different kinds of volcanic or extrusive igneous rocks. So when we try to classify or characterize these rocks to figure out what we're looking at, one thing that we're going to look at a lot is what we call the grain size, or basically the size of the different mineral fragments. So a couple slides ago, I showed you a picture of granite where you could clearly see little white flecks and little black flecks and little brown flecks all mixed together. And so in that case, that rock had a fairly large grain size where we wouldn't need some sort of microscope to be able to see the different mineral grains or mineral crystals in the rock. However, in other cases, those grains might be so small. So I'm sure we've all just seen like matte gray looking rocks, and that's because all the minerals in those rocks are so small that we can't see them with our naked eye. So when we're trying to classify rocks, we're going to be looking at the grain size, we're going to be thinking about how big the grains are, and then we're going to be thinking about the colors of the grains and different kinds of like luster characteristics or other mineral characteristics that might help us understand which minerals are actually in the rock. So we know that some minerals are more felsic in character, some are more mafic in character, and knowing the composition of the minerals inside the rock might help us ID the rock and understand then how the rock may have formed. Of course, color is an important characteristic as well. So this is going to refer to the color of like the individual mineral pieces that we can see them, but also kind of the overall color of the rock. And so remember, this term felsic refers to these kinds of minerals that are silica rich in nature, aluminum rich in nature, and kind of metal poor in nature, so not having a lot of things like iron or magnesium in them. And so those minerals themselves tend to have a lighter coloration, but then rocks that are rich in those particular minerals are also going to be considered felsic in character. And sometimes we would refer to these as rhyolitic as well, which refers to the kind of extrusive igneous rock that can form from this felsic type molten rock material. So felsic rocks are rocks that are like rhyolite, as I just mentioned, which is an extrusive kind of ashy rock that would form from a volcanic eruption. And then granite, we've already talked about, is an intrusive rock. So this term felsic doesn't tell us whether the rock formed underneath the earth or on top of the earth, but what it does tell us is that it's made up of these kinds of minerals that are listed below in this diagram, such as quartz, such as mica, such as feldspar, and only with a little tiny bit of maybe some amphibole minerals. And if you can imagine what these minerals look like, or we'll look at them more in lab this week, these are typically all lighter colored minerals. So unsurprisingly, the rock itself is going to have an overall lighter color. On the other end of the spectrum, we can have mafic rocks that are made up from mafic type minerals. And so mafic rocks might be something like basalt, which is a rock formed from lava flows, or gabbro, which is a rock that's formed underneath the earth like granite, but it has a much darker coloration than granite. And that darker coloration comes from the fact that it's made up of different kinds of minerals. It's made up of things like pyroxene, amphibole minerals like hornblende, maybe even some olivine, and then maybe some plagioclase, feldspars. So these minerals down here are usually darkish gray colors, blackish colors, and greenish colors. And so the minerals themselves and then the overall rock is going to have a different look to it. It's going to be darker in color. And then intermediate minerals, which sometimes we refer to as andesitic, and especially the melts, like the lavas, we can refer to as rhyolitic, andesitic, and basaltic that form these rocks. Anyway, they're going to have an intermediate composition. And so if we can identify what these rocks look like, then we can understand what's inside these rocks. And then that might help us understand when and how these rocks formed and where they formed. And so when we're trying to have this perspective about understanding the history of the earth, understanding how all these different things form and what they're made of is going to be kind of an important set of information that's going to help us interpret landforms and then past Earth's history. So one of the important things that affects the look of rocks is the rate at which the melt cools down. And so generally, if you are losing heat very quickly to the environment, then you're going to be cooling down very quickly. And this usually happens when the environment around you is much colder. So when lavas spill out onto the Earth's surface, and especially if they spill out onto the Earth's surface in the deep ocean where it's very cold, there's going to be a really rapid heat transfer from the lava to the air or to the water, which is going to result in fast cooling, and that's going to result in the formation of crystals from this melt that are very small. They don't have enough time to grow into large size crystals that are easy for us to see. And so when we have these rocks that form in this rapid way on the Earth's surface, we typically cannot see the crystals or the grains with our naked eye. And so that is characteristic of these extrusive igneous rocks. And there's a picture down here on the right of pillow basalts. Basalt is a type of extrusive mafic igneous rock, and pillow basalts in particular form underneath the ocean when lava spills out from these submarine volcanoes, and then it cools very, very rapidly into these big blobs of this kind of dark black rock. So it's a little bit hard to see the color underneath the water, but you can kind of see these blobs of cooled off lava. Of course, it's not only a factor of the environment, or, well, the temperature of the surrounding has a big impact on this. So the bigger temperature difference, the faster the heat is going to be lost, which is what I just described. Hot lava, cold water, that's a big temperature difference, a big loss, as opposed to granite, which is cooling down underneath the earth in a very hot environment like cooling down cookies in an oven, they don't cool down very quickly. Cooling down cookies in a freezer, they cool it down a lot faster. So that can make a difference. And then also different kinds of materials that are surrounding them may just be different level insulators in terms of how quickly they pass heat away. So not only is it a temperature difference, but it could literally just be a material difference. So in general, air and water are very poor insulators. So they're gonna pull and pass heat quickly away from a lava or magma, whereas rock underneath the earth is gonna be a much better insulator. And so that's an additional reason why something like granite or gabbro that forms underneath the earth would form much more slowly and have the opportunity to grow larger size crystals in that slow cooling process. Okay, so these intrusive rocks, like granite, like gabbro, form when magma that is less dense than the rock around it starts to buoyantly rise through different cracks in the environment. And so you can kind of think about this is if you have your toes and you step in like mud or wet sand, the less buoyant, more liquid-like material, the mud will start to move up through your toes. So that's kind of what happens where like the solid rock in the environment of the magma will start to kind of sink while the more buoyant liquid will start to rise. And then in some cases, that liquid will make it all the way up to the surface and come out of a volcanic vent. But in other cases, it will start to cool and freeze when it reaches a cooler environment near the surface. Or if for some reason the heat that was coming into that area through a magma plume or whatever starts to move, and so the material will cool down even at a lower depth. So those are some reasons why we might have intrusive igneous rocks form, why we would have rock that was melted at one moment and then cooling off enough to freeze at another moment without getting up to the Earth's surface. So what this would look like conceptually is we have the Earth's surface, we have different rock layers underneath the ground, and then we would have magma that would come up underneath the Earth's surface into a magma chamber, and maybe perhaps, or maybe in the past, this was connected to some sort of volcano that would have existed on the surface that has long ago been eroded away. And this was a chamber that had a bunch of magma. So these are called intrusions because they kind of intrude into what's called country rock, or rock that was around in the environment before. And when they freeze down, we refer to them as plutons. So sometimes plutons contain little fragments of older country rock that kind of got melted off into the magma chamber and then kind of froze up without melting. These are sometimes called xenoliths, so you might see this kind of thing in an intrusive igneous rock. But knowing these terms about intrusions and plutons and country rock are kind of good terms to know when we're thinking about intrusive igneous rocks. So a place that you might have seen this in the environment before is in the Sierra Nevada, which is where we live. We're in the very kind of northern part of the Sierra Nevada range, which is this big granitic mountain range that runs along a lot of the eastern border of California. So about 100 million years ago, or from about 140 to 80 million years ago, there was a big volcanic range that was above the area where we live today. And this was created from subduction of an old plate called the Farallon Plate off the kind of coast of California. We'll talk more about plate tectonics later. But that created magma that rose up to form these volcanoes. And then deep down underneath the volcano, so like many, many miles below the surface, were these big magma chambers. And over time, the subducting plate that was fueling this magma formation and fueling these volcanoes completely disappeared beneath the North American plate, and so kind of lost its heat engine or its energy engine. And so the magma that was still in these magma chambers cooled down to form granite. And over the last 100 million years, the wind and rain and glaciers, et cetera, have eroded the overlying landscape away. And today we're walking around on the surface of these old granite magma chambers, or plutons. And so these are these intrusions, and they're no longer underneath the earth. They're now on the surface of the earth, but that's because the rock that used to be on top of them has been eroded away. And so things like Half Dome and other granitic domes like Grizzly Dome in Plumas County. If you go to places like Tahoe, you'll see all this big granite, sometimes referred to as the range of light, because granite is generally a very light colored rock. And so it's kind of a very bright white type of rock in the environment throughout the Sierra Nevada. So this is an example of an intrusive igneous rock. Another place where you might have seen these rocks that kind of cool off underneath the earth are in what are called volcanic necks. So these volcanic necks are kind of on the border between intrusive and extrusive igneous rocks, because they do form below the Earth's surface. They form inside of a volcano, but they form much closer to the Earth's surface compared to the rocks down in those magma intrusions that turn into plutons. And so there might be some compositional differences in the rock, but in either case, these rocks that form in volcanic necks, just like the rocks that form in the magma chambers, tend to be very sturdy, strong rocks that don't break down well over time. And so as the overlying landscape erodes away, often these volcanic necks will really stick up and be prominently visible even when the rest of the landscape has eroded away. So Devil's Tower is a very famous example of an intrusive igneous rock that's kind of sticking up, this volcanic neck in Wyoming. There's some of these around here, even in Plumas County. And here's a picture of kind of a volcanic neck visible from Sonora Pass, lower down in the Sierra Nevada. Okay, so those are some examples of intrusive igneous rocks. Extrusive igneous rocks form from the fluid that makes it up to the surface. Once that fluid comes up to the surface and starts to lose different gases to the atmosphere, we refer to it as lava as opposed to magma. And this lava can have very differing characteristics in terms of viscosity. And viscosity refers to how easily something is able to flow. So if it's very viscous, that means it's really sticky and it doesn't flow well. Where if it has low viscosity, it's very fluid. So you can think of like honey as being viscous and like water as being low viscosity. And so generally what happens is as the melt starts to come up to the Earth's surface, first of all, it encounters an environment that's a lot colder than the environment underground. So if you can think about like cooling off melted chocolate or something, it's going to start to freeze up as it cools down. The same thing happens with this lava. At the same time, these gases that are dissolved in the magma underground that we refer to as volatiles, that's just a word for these gases, they start to come out of the fluid because they're not under as much pressure as there was before. So you can think of if you had like a soda with a pressurized top on that you can't see the gases, and then you take the top of the soda off, you depressurize the environment, and all these gases or volatiles start to bubble up out of the soda. So the same thing happens with lava as well. And as it cools down and loses these dissolved volatiles, both of those things contribute to an increasing in the viscosity of the fluid, or an increasing in the stickiness or resistance to flow of the fluid, which eventually causes these fluids to freeze up and form extrusive igneous or lava rocks or volcanic rocks. So in many of these cases, we can actually see the evidence of the degassing that takes place. And that's why we have these bubbles that exist in many igneous rocks, though not all igneous rocks. But this is a great clue that helps us identify that this is a process that was occurring on the Earth's surface. We would never see bubbles in rocks that formed deep down underneath the Earth under great pressure. So if we ever see these kinds of what are called vesicles or air bubbles in a rock, that's a really good clue that that is a rock that formed in a volcanic environment at the Earth's surface. So again, as we start to be able to identify these rocks, we can start to learn about the Earth's history, what was going on when these rocks were forming. Just like in the case of intrusive rocks, the rate of cooling has a big impact on the way that the rock looks. Rocks that cool off underwater tend to cool much more rapidly than the rocks that cool in the air. So lava has an ability to flow much farther from a volcanic vent if it erupts on land versus in the ocean. Also, some of the compositional factors of the magma will determine how flowy the magma is. And so it could have different looks. And again, when we are identifying these rocks and looking at things like this pillow structure or looking at this really sinuous, long lava flows, this can help us understand, was this environment in a submarine environment? Was it in a land environment when it formed? We can also look at different kinds of chemical and mineral markers for that. But these are all just kind of like forensic ways that we can start to understand the history of the Earth. Another kind of classic extrusive or lava rock look is basalt, which is a very common type of extrusive igneous rock. Often cools down to form these columnar structures or these column structures. So you may have come across this kind of thing before. This particular picture is in Hawaii, but there are some of these examples in Plumas County. And then there's some more kind of famous examples down in the Mammoth area. This is called Devil's Postpile, if you've ever been here before. And there's other kind of Sierran examples of this as well. So again, all of these kind of structures, volcanic structures, are helping us understand about the history of what was going on. This was a basaltic lava flow in an extrusive volcanic environment. So even if there's not a volcano here today, we know something about what was going on here in the past. And then another common type of extrusive igneous rock is formed when the lava that comes out of the volcano freezes up very, very quickly near the vent of the volcano, near the top of the volcano. And then as it freezes, it kind of starts to plug up the volcano. And then as more lava and magma starts to push up underneath of it, it builds up a lot of pressure, and eventually it kind of blows the top off, kind of like they often use the champagne, popping the champagne analogy here. And all these little pieces of frozen, like glass and frozen tiny pieces of rock that have cooled off very, very quickly near the volcanic vent are blown up into the air into this big ash cloud. And as that ash kind of settles down on the land surface, it can form these big ash deposits. And these ash deposits are great repositories for fossils. We'll talk a lot more about fossils later. So in most cases, igneous rocks are not home to lots of fossils because the really hot character of magma or lava would just destroy evidence of living organisms. But when this ash falls out of the sky very quickly in these severe volcanic eruptions, it can capture lots of living organisms and fossilize them. So anyway, this type of rock is called rhyolite. We have a lot of this in Plumas County as you drive between Quincy and Gray Eagle, or Quincy and Portola. You'll see a lot of these kind of ash deposits from things like the Bonta Formation, which is about, I think, like a 5 million year old formation along the middle fork of the Feather River there. This particular example is from New Mexico. And you'll often hear this referred to as a rhyolite or a rhyolite tooth. But anyway, it's this kind of usually light colored, because it's felsic in nature, deposits of ash. So not a lava rock, but still a extrusive volcanic rock. Okay, that's a good stopping point.